The goal today is to use scientific notation to read and write numbers in scientific notation, order numbers in scientific notation, and multiply and divide numbers in scientific notation. So standard notation is the traditional way of writing a number using standard place value. So for example, if I wanted to write the number 3,165,000, I would write it like that. Scientific notation is a way of expressing a number as a power of 10. And it looks like this. C times 10 to the n. And so you'll see that we've got our old-fashioned multiplication symbol, we've got a power of 10, and we've got an exponent. And there are some restrictions. So the first restriction is that the C value has to be less than 10, but greater than or equal to 1. And so an easier way to think about that is it's going to be something point something something. We've got a decimal, and then there can only be one digit before that decimal, and that digit either has to be a 1 through a 9. So scientific notation is going to heavily involve decimals, and whatever we put before the decimal point, so it can be like 1 point something, 2 point something, and so on, all the way up to 9 point something. It won't matter how many digits follow the decimal point, but what's key is that prior to the decimal point, there can only be one digit, and that digit either needs to be a 1, 2, 3, 4, 5, 6, 7, 8, or a 9. Then we're going to have our power of 10, which is our n, and n has to be an integer, which means that n can either be positive or negative, but it can't be a decimal or a fraction. If the power of 10 is positive, it's going to tell us to move the decimal n spaces to the right. And if the power of 10 is negative, it's going to tell us to move the decimal n spaces left. And so actually what I'm going to do now is I'm going to hold off on these examples, and we're first going to see how we can get numbers from scientific notation into standard notation. And so to do that, I'm going to go to page 2 of the notes. So go ahead and turn the page. So here I've got a set of examples that are written in scientific notation. They're written, if you look, they've got one digit before the decimal place, and some of them have multiple digits following. This one happens to only have one. But again, the key is if you look at the placement of the decimal, they all only have one number prior to the decimal place. That'll be important when we go back to page 1. And so if I look at my number, my first example, 2.0075 times 10 to the 6th. So I'm going to look at my power of 10, which is 6. It's positive, so I know I'm going to be moving my decimal to the right, and it's 6, so I'm going to be moving it 6 times. So I'm just going to take my decimal, and I'm going to go 1, 2, 3, 4, 5, 6. And so if I actually add some swoops in there, I've got 1, 2, 3, 4, 5, 6. Now I've got 2 empty spaces that I need to fill, so I'm going to fill those with zeros. And so on my line, I'm just going to work backwards. So I've got 0, 0, 5, 7, 0, 0, 2. And now I'm going to work my way backwards and add my commas. So that number is really 2,007,500 if it was written in standard notation. But in scientific notation, we had read it as 2.0075 times 10 to the 6th. If I look at my second example, I'm going to look at my power of 10. It's negative, which means my decimal is going to be moving to the left, and it's 4. So I'm going to move my decimal to the left 4 times. 1, 2, 3, 4. There's my decimal, and all those empty spaces, which there's 3 of them, are going to get filled with zeros. So 1, 2, 3 zeros, 1, 6, 8, 5. That would be the number in standard notation using traditional place value. Pause the video. I'd like you to try these 3 examples. Press play when you're ready to check your answers. So on this example, I'm being asked to move my decimal 5 times to the right, which would leave me 1 empty space, and so that's 702,350. This time I'm moving it 7 spaces to the left, which means I would have 6 zeros. If I wanted to actually name this number, I'd have to count up my place values, so tens, hundredths, thousands, 10,000s, 100,000s, millions, 10 millions, 100 millions, billions, 10 billionths. And so I believe that would be 3,096 10 billionths. but I usually just say 0.000000396. And then this one's asking me to move my decimal 4 spaces to the left, and so I get 0.00045. So at this point, we're going to go back to the first page. So pause the video, turn back to the first page, and now we're going to work on putting numbers from standard notation into scientific notation. And so if you're thinking at this point, why is scientific notation useful? Well, first of all, you hear the word scientific. It's something that mainly scientists would use. And if you think about scientists that might study really, really big things like distances in space that are hundreds of millions of miles or billions of miles, or atoms that have, teeny tiny radiuses or masses or diameters, this is going to be a way for scientists to express numbers that are either really, really big or really, really small. So they don't have to worry about all of these zeros kind of getting in the way, because if you had to calculate with these numbers, we want to try to be more efficient. And so scientific notation is going to allow us to do that. So if my goal is to put this 42,590,000 in scientific notation, I have to make sure that I meet the criteria that I set up here. So it's going to be something times 10 to the n power. And the key is that that first piece has to be between 1 and 10, but it has to be less than 10, but it could also be equal to 1. So the first thing I want to do is I want to move my decimal point. And so currently, the decimal point, which is invisible, lives at the end of the number. And so that's where it would be. And according to this, I want to move the decimal point so there's only one digit to the left of it. So if I could grab my decimal point and move it over, what I would do is I would drag it back until there's only one digit to the left of my decimal. And so that would be between the 4 and the 2. And so my decimal point is going to live right there. So I've got 4.259. Now I don't need the rest of the zeros, and that's kind of the whole, no pun intended, point. So now the question is, if someone were to walk in from the outside and place their finger here, we know that the original number was really 42,590,000. They're currently looking at the number 4.259. We would need them to move the decimal in this direction. We want the number to get bigger. And the question is, how many times would they need to move the decimal in that direction to get back to 42,590,000? And so we can come here and count. So I'm going to put my finger here, and I'm going to count until I get back to the original decimal point. So it's 1, 2, 3, 4, 5, 6, 7. So I know my power of 10 is going to be 7. So times 10 to the 7th. And whether or not it's positive or negative is going to depend on the direction that, not that we moved it, but that this would need to go in order to get back to this big number, and it would need to move to the right. So I'm going to keep it as a positive exponent. And if you're wondering why that is, think about that. If that was negative, then someone would put their finger here and they would start to go in this direction. And that would not get them back to this original number, 42,590,000. So 42,590,000 is in standard notation, but in scientific notation, it's going to look like that. So if I look at my next example, which is 0.0000574, so my first task is to take the decimal point, which is here. So here it was invisible. Here it's not invisible. But I want to move it so that way there's at least one digit to the left of it, which if you're looking at that now saying, well, yeah, there's a 0 there. It has to be 1 through 9. So I'm going to move my decimal over here and put it between the 5 and the 7, because now there is one digit before the decimal point, and it's a 5. So that's going to give me, sometimes I call it like the stem almost. So 5.74 times 10 to the question mark. And so we've got to find our exponent. And so if someone were to put their finger here and you want them to get back to this really small number, would we want them to move in this direction, or would we want them to move in this direction? And so I can actually see if I put it on the original, the decimal lives to the left. And specifically it lives 1, 2, 3, 4, 5 spaces to the left. So 5 spaces, power of 5, but it's moving in the left direction, so it's negative. 5.74 times 10 to the negative 5th would be that number in scientific notation. You are going to pause the video to try the next 3 examples. Press play when you're ready to check your answers. So on my first example, 539,000. So here's my invisible decimal point. So I need to bring it back so it's between the 5 and the 3, one digit on the left. That gives me 5.39. And so if my decimal is here and someone were looking at that, to get back to the bigger number of 539,000, they would need to move it 5 times to the right, so an exponent of positive 5. For 267,500,000, here's my invisible decimal point. I need to bring it back so there's only one digit to the left. And so then someone looking at that would need to move it 8 times to the right in order to get it back to 267,500,000. 4.000486. First, the decimal would move between the 4 and the 8, and someone looking at that would need to move it 4 times to the left. Because it's left, it's going to be a negative exponent. So at this point, we're going to go back to page 2, and we're going to finish the examples on the bottom. So the next goal that we want to be able to accomplish is to order numbers in scientific notation. So you have two options. Option 1 would be to take your 3 different numbers and put them in standard notation and order them like you always have. But that's not what the standard is assessing. And so instead, what we want to do is to take the numbers that aren't in scientific notation and put them in scientific notation. So 103,400,000 would become 1.034 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. That's one of my numbers. My next number is 7.8 times 10 to the 8th. And then my last number would be 8.076 times 10 to the 1, 2, 3, 4, 5, 6, 7. And so now as I'm ordering, the first thing that I'm going to notice is that I've got 1 power of 10 that's less than the others. And so what that tells me is that 8.076 times 10 to the 7 is going to be less than my other numbers. Then the next two have a matching power of 10, 10 to the 8th. And so now I'm going to look at the C part to see which one would be the smallest. And 1.034 is smaller than 7.8, and so then that's the number that's going to come next. 1.034 times 10 to the 8th, and then 7.8 times 10 to the 8th. Now the last thing that I want to do is I want to provide the numbers in the same format that they were provided to me. This number was given in scientific notation. This number was given as 103,000 or 103,400,000. And this number was given as 80,760,000. But again, in the real world, you could always have taken this one and changed it to standard notation in order to compare, but that's just simply not what you're being asked to do. Try this example. So you've got 93 million, 9.2 times 10 to the 6th, and then 9,028,000. Pause the video, press play when you're ready to check your answers. So here I changed 93 million to 9.3 times 10 to the 7th. This one was already in scientific notation, and 9,028,000 was 9.028 times 10 to the 6th. So 10 to the 7th is my highest exponent. That's going to be my biggest number, which again I put back into its standard format because that's how it was given to me. And since these have the same exponent, I'm going to compare their C values, and so 9.2 would be bigger than 9.028, and so 9,028,000 compared to this would actually be 9,200,000, and then compared to 93 million. The next thing we need to be able to do with scientific notation is to multiply or divide numbers that are in scientific notation. So again, you could potentially put them both in standard form, but then you might open yourself up to having to type in numbers with many zeros either at the end or the beginning. So the first thing I'm going to notice is that this is multiplication, and this is multiplication. So I'm multiplying 4 things, and because multiplication is commutative, what that means is I can change the order, and so I could first multiply 8.5 times 1.7, and then I can also multiply 10 to the 2nd times 10 to the 6th. And the reason that this is in this chapter is because what we just discovered is that if you're going to multiply 2 items with the same base, the shortcut tells us I'm allowed to add their exponents. So as a result of that, 10 to the second times 10 to the sixth is going to be 10 to the eighth. And then off to the side on my calculator, I'm typing in 8.5 times 1.7, which is going to come out to 14.45. Now here's where it gets just a little bit tricky. This seems like it's in scientific notation because it's something times the power of 10. But don't forget that in scientific notation, this decimal can only have one digit preceding it. And so right now I've got 2 digits before it. And so what that means for us is that the decimal point should really be between the 1 and the 4. But that's going to affect my power of 10. And let's see how. So if this were the spot that the decimal point was allowed to be, this exponent tells me that my decimal should move 8 spaces to the right. But since the decimal needs to be pulled back 1 space, and this says it's 8 spaces to the right, I'm taking the decimal 1 space farther away from its final destination. So again, here, this tells me that I would move it 8 spaces to the right, but oh, wait, you were supposed to start right here. And so now that means that the decimal is 9 spaces from its destination. And now that's officially in scientific notation because remember, for scientific notation, there can only be 1 digit prior to the decimal space. Let's look at our next example where we're squaring everything inside the parentheses. And again, this is going to follow our rule of exponents. And so my rules of exponents says that everything inside the parentheses is going to receive the second power. So that means I'm going to raise 1.5 to the second power, and I'm also going to raise 10 to the negative third to the second power. But remember, if I'm exponenting something, I'm allowed to multiply their exponents, which means it would be 10 to the negative 6. And so again, if I on my calculator type in 1.5 times 1.5, I'm going to get 2.25 times 10 to the negative 6. And I don't have to worry about making any adjustments because there's only 1 digit prior to the decimal place. So let's scroll down and let's do a division example. And so here I'm dividing 1.2 times 10 to the fourth divided by 1.6 times 10 to the third. And so what I'm allowed to do is I'm allowed to divide 1.2 times 1.6. I could either do that in a calculator, or I could say 1.2 divided by 1.6 would be the same as dividing 12 by 16, which would reduce to, if I divide top and bottom by 4, 3/4, which is 0.75. So again, if you divide 1.2 by 1.6 on a calculator, you're going to get 0.75. And then I'm also allowed to divide 10 to the fourth divided by 10 to the third. But remember, if I'm dividing and the bases match, I'm allowed to subtract their exponents, which means I could do 4 minus negative 3, which would give me the power of 7. And so now, if I'm looking at this, it looks like it's in scientific notation. It's something times something to the 10 to the power of something. But I don't have any digits prior to here. Actually, if I had a digit, it would be a 0. And remember, this number either needs to be a 1, 2, 3, 4, 5, 6, 7, 8, or 9. So that means my decimal point isn't in the right spot, and my decimal should be here. But before I do that, I first want to say, okay, if the decimal could have been here, which it can't, but let's say it could, this exponent would tell me to move it 7 times to the right. But it's not in the right starting spot. So by bumping it over and now putting it between the 7 and the 5, I'm moving the decimal 1 place closer to its final destination, and so now it's only 6 spaces away. So even if if someone came in and said, let me move this 7 times and let me move this 6 times, they'd get the same answer. It's just that this one's in scientific notation because there's only 1 digit prior to the decimal, and this one has the wrong digit prior to the decimal. So what you're going to do right now is you're going to pause the video and you're going to complete the remaining examples. And so there's 1, 2, 3, 4, 5, 6. Press play when you're ready to check your answers. So on this first one, I multiplied 5.7 by 2.6 to get 14.82, and then 10 to the third times 10 to the fourth is 10 to the seventh. But there's 2 digits before the decimal place, so I need to pull the decimal back 1 spot, which is causing it to get 1 step farther away from its destination. So that's why the exponent's going to go from 7 to 8. On the next example, 2.4 times 2.4, because it's getting squared, is 5.76, and then 10 to the negative fourth to the second is 10 to the negative eighth. There's only one decimal before, so I don't have to adjust at all. Same thing here, 1.3 squared is 1.69, and then 10 to the negative 5 squared is 10 to the negative 10th, already in scientific notation. 1.1 times 4.2 is 4.62, 10 to the 7th times 10 to the 2nd is 10 to the 9th. Then on my other division one, I divided 4.5 by 1.5 and got 3, which if that looks funny, you can write it as 3.0, so then you can really see that there's one digit before the decimal place. 10 to the negative 5th divided by 10 to the negative 2nd, because I'm dividing, I can subtract the exponents. So 5 minus negative 2 is my 7th exponent. And then here, if I divide 2.4 divided by 2.5, I'm going to get 0.96, and then these are dividing, so I can subtract. 5 minus negative 4 is 9, but there's no digit before the decimal, and so I've got to move it this direction, which means it's getting one place closer to its destination, and so that's why the exponent goes from 9 to 8. So the last thing that I want to be able to do is to use scientific notation in real-world situations, and so here I've got a capillary, a venule, and an arteriole, and it says let R1 be the radius of a venule, let R2 be the radius of a capillary, and it asks me to find the ratio, so right away I know that means I'm setting up a fraction of R1, which was the venule, to R2, which was the capillary, and the venule radius was 1.0 times 10 to the negative 2 divided by a capillary, which was 5.0 times 10 to the negative 3, and so then if I were to divide those, 1 divided by 5 is going to get me 0.2, and 10 to the negative 2 divided by 10 to the negative third, if I subtract negative 2 minus negative 3, would be 10 to the first. But again, not in scientific notation, and so I'd actually have to move the decimal one place closer, which means 2 times 10 to the 0. But oh wait, 10 to the 0, anything to the 0 power is 1, and so then 2 times 1 would just be 2, which also makes sense because on that particular one, remember this would mean like move it one space to the right, this would mean move it 0 spaces. So my answer is just going to be 2, and so what that tells me is that my ratio, my venule radius is 2 times the size of a capillary radius. And so then it asks us to find the ratio of area 1 to area 2, and this time the area 1 is the area of a venule, and this is the area of a capillary. And so to find area of a circle, we do pi r squared over pi r squared, but this is our venule and this is our capillary. Now you can see right away, pi's are going to cancel. And so then radius of a venule was 1.0 times 10 to the negative 2 squared over 5.0 times 10 to the negative 3 squared, which would mean, if I bring this over here, 1 squared is 1 times 10 to the negative 4, that's my numerator. 5 squared is 25 times 10 to the negative 6. So then I'm just going to divide. 1 divided by 25 is 0.04, and then 10 to the negative 4 divided by 10 to the negative 6 would be 10 to the second. And so then if I were going to put that in scientific notation, I'd have to actually move it 2 places closer, which means it's getting 2 places closer. And so it'd be 4 times 10 to the 0, but again, 10 to the 0, anything to the 0 power is 1, so 4 times 1 would just be 4. And so then what that means is the ratio of the area of a venule compared to the area of a capillary. A venule is 4 times the size.